The first OS resource management task we'll look at is that of managing memory. Remember, it's sometimes referred to as core memory due to those old magnetic cores. Now, it's closely related to processes and I/O devices, as we'll see, but we have to start somewhere. So we'll talk about sharing memory. Let's look back at what CPM looked like. Well, obviously in memory, if we have an operating system, we need some space for that, and it's probably the first thing that's going to get going. So we'll start it at memory's location 0, so it starts up immediately. Then our application program will live someplace else, and just for yucks, we'll call that 10,000 decimal for right now. And here's a typical application program. You should recognize this from PEP 8. We've just got a word of memory, and we're going to load it, add to it, and store it. And if we pump that through the PEP 8 assembler, it'll come out with something like address X would correspond to the third byte of memory, so the PEP 8 assembler would produce an address of 3 in those two locations with the instructions. However, that's going to be a problem. Even though our logical address, just looking at our program, is 3, the physical address that we're actually going to see in memory is 10,003 because our first location corresponds to location 10,000. Now, we could ask the loader to take care of this for us. It knows we're being loaded into a location 10,000, so it could look for every address in the program and change all the 3's to 10,003's. However, that means the loader really needs to know a lot about the instruction set of our program. In fact, almost disassemble it while we're doing it. That's a real pain. So, although that was done in some of the original operating systems, a newer technology depends on a little bit of help from the hardware, and this is what's used today. We've actually seen this in PEP 8. This is where we use the base register. So, when the operating system loads our program into memory at location 10,000, it also loads the base register with the value of 10,000. Then, whenever it needs to compute a physical address, it looks at the logical address stored in the program and automatically adds the contents of the base register before going out and addressing memory. That gives us the physical address that we need. Now, the next thing that happened in computers is we wanted to be able to run multiple programs at a time. Now, we saw that the original operating systems were perfectly happy with 64K of memory, and that led us to 16 bits of addressing. So if we had a whole bunch of programs that worked in 64K, what we could do is break memory up into 64K chunks. That way we could put a whole bunch of different programs in memory, each thinking they've got their own 64K chunk. We could load 3 processes, for example, in these 3 different areas. When the first process is running, the operating system loads the base register with address. When the second process runs, his address is loaded into the base register. And when the third process runs, he gets his address. So the operating system, when it transfers control to a particular process, simply loads the base register, and everything works like a champ. Each program thinks it's running in its own dedicated computer starting at address 0, and they end up sharing the memory very nicely. Now, the operating system does have to do some work here. In particular, he's got to remember where each of those processes got loaded so he can set the base register up appropriately at the right time. However, we still have a problem. Can we run a bigger process, one that uses, 32 bits worth of memory address? Well, not in this fixed partition scheme where everything is 64K. So that led to the next innovation, fixed but variable size partitions. And I could make a big partition where I could run big processes. He's perfectly happy. I load up a nice value in the base register, and my big process can run like a champ. Now, this leads to an interesting question. If a new process shows up that I want to run, and he's not big, should I go ahead and blow away the big partition and use it for this small process? After all, another big process could be coming right behind it. Ooh, but it came behind it. Maybe he should go second because he's second in line. Well, maybe he's big, so he should use the big partition while it's there. So the operating system has to make a decision. Who gets loaded? Well, maybe if I got smarter, I wouldn't have to make these tough decisions. So the next generation of operating systems used what are called variable partitions. Instead of locking everything down into fixed partitions, we use just enough memory to fit a given process. Process 2 takes a little bit more than process 1 does, and realistically, most of these systems worked on a multiple of some minimum block size. We'll use 8K here in this example. This means that lots of processes can run, and I don't waste any memory by using a maybe 8K process in a 64K block. I can get more work done with no more memory. The base register works just like it used to. However, I've now got an additional consideration. Process 1 could address some memory past his 8K boundary with his 16 bits worth of address space, but if I let him do that, he's going to be trampling all over process 2's memory. I've got to figure out a way to stop that. The typical solution is something called a bounds register. So I look internally to see what would be the last legal address he could use. And as long as process 1 is executing, if I ever see an address coming out across the address lines bigger than that bound register, I throw him right out of memory on his ear because he's trying to tromp in somebody else's part of the sandbox. He's not sharing nicely. The bounds register needs to get reset every time I start a new process, just like the base register, to keep everybody out of each other's way, even if they're doing it accidentally. So the operating system's job has now gotten a little bit bigger, and the hardware has to assist me as well because it's got to let the operating system know when I've trampled across one of my boundaries. I've also made my decision-making life a little bit more difficult because now processes can disappear in random orders and leave different sizes of blocks available for my competing resources. Should I go ahead and put process 6 in here, or should I maybe wait for one of those smaller processes to go away? Well, they went away. Should I load them in the bottom? Should I load them in the top? Who's going to go away next? If process 3 goes away next and I load process 6 up there in the top, then I've screwed my other big process. But if I put him down at the bottom and the big process goes away next, then my other big process is okay. So which one do I do? Particularly if I don't know which one of those processes is going to finish in advance. I could try to guess. Oh my job is getting more difficult all the time. So I need a couple of strategies that I can use. 3 that have been typically used in this kind of environment are called best fit, first fit, and sort of inaptly named worst fit, which really means find the biggest place. So when I look at process 6, I would try and find the open chunk of memory that's closest to his size. First fit is just like it sounds. I start at the beginning of memory, and as soon as I find a chunk that fits for him, that's where I stick it. And biggest is find the largest chunk of memory and put him there. Now that sounds a little counterintuitive, but one of the problems with the other 2 algorithms is sometimes I can end up with a lot of little teeny tiny chunks of memory floating around that aren't really big enough for anybody. If I chew up a big chunk of the memory, leaving a big chunk of the memory, I've got a better shot of being able to get somebody else to work in it. Now one other strategy I could use would be to squeeze everybody back together, which makes room enough for a big process. However, that's going to take time, and everybody's going to have to wait while I'm shuffling all that memory around. So we have a question here. Where to load a given piece of memory? First fit is simple to implement, yet it may waste space. So that's not fair to people who are waiting for memory that's available, but just in the wrong place. Best fit, better chance of getting people in, but it may leave a lot of small useless spaces over time, and so later coming processes might get. Worst fit could waste even more space if we get unlucky. So maybe I should reserve large partitions for large processes. Let the smaller ones wait. Well, that's nice if you're a large process, but then I've got lots of memory just sitting around, potentially, where small processes are waiting to get something. Well, I could also do the compaction and move things around, but that takes time, and everybody's going to rate. So there's no solution that's perfect, and it often depends on what you're trying to accomplish. what's fair to you may not be fair to someone else. I also have a question of who to load. Should I load the first process I can find that's waiting that fits? Well, if I do that, bigger processes may wait an awfully long time. So maybe I should load the first process in line as soon as it fits. Well, that means he's blocking the smaller processes that might be able to get through quickly. This is starting to sound like a super. I could reserve the large partitions for large processes and let the smaller ones wait, and load them if no big ones are around. Or we could do the supermarket express lane. Small partitions reserved for small processes, and big ones wait even if there's room available with a bunch of small ones. So I only load the big ones if no small ones are waiting. Still complicated. Maybe I can get even smarter and make my life simpler. What if I could just bust process X up into two pieces? Then he'd fit. Hoo-ha! However, my translation now from logical addresses to physical addresses gets kind of tricky. In the first part of process X, I'm going to have to set my base register to 72K. In my second part of process X, I'm going to need to set it to 144K. And then I still got to worry about the fact that he might go over his boundaries anyway. So anything over 48K, I've got to blow him out of the water. This is actually a variation on what we do today in most modern operating systems. It's known as paged memory management, and I split every process up into a fixed size of blocks, typically 512, or some cases 2048 or even 4096. And then I slot those pages into memory wherever it happens to be available. And now I know the most memory that I'm going to waste is the number of pages that are free in any specific chunk. So let's walk this through. I start my base register in page 0 when my program number 1 begins processing. When he goes into page 1, however, look what happens. His address is still legal from a logical perspective, but if I used that address, I'd be in the middle of process 2. No good. Somebody needs to catch that and stop him. Well, and in fact, that's what modern hardware does. It generates what's called an interrupt to the operating system to say, hold on, I think you better take a look at this. You don't want to necessarily blow this guy out of the water, because even though he's over his edge, he's still legally in his own logical address space. You need to do something. Well, and in fact, what the operating system, of course, needs to do is recognize that he's gone to page 1 of his own address space, and under the covers, switch the base register, so he's now operating in process 1. So this interrupt, when going across a page boundary, is what allows us to implement a paged memory management solution. Without some help from the hardware, you really can't pull this off. Interestingly, Intel was one of the first to put this in their chips, so they grabbed a huge market share of people who were trying to do fancy things like this in their operating systems. Now, this gives me an even better idea. Rather than waiting for my whole program to load, since I got this stuff working anyway that he interrupts when he goes beyond his page boundary, I'll just bring in the pages as needed. So when he starts executing in page 0, I'll load page 0, and under the covers maybe I'll try and get page 1 in there when I'm not doing anything else terrible. However, if he gets to page 1 before I'm there, again, I need an interrupt. This interrupt is called a page fault. I'm not ready to actually transmit into something that's into a different location. I have to actually make sure that that piece of program code gets loaded. So a page fault happens when a page needed for a process is not currently in memory. It's out on disk someplace, so I read it from the disk into some free frame and then let things go on. Page 1 and page 2 can get loaded when he's needed. Now what happens if another process comes along? Well, if I can bring his pages in as needed, I can bring his first page 0 in. Now, notice something that's happening here. I don't have everybody all in memory at the same time, but there's not enough room to fit everybody in memory at the same time. So demand paging lets me work here, but it leads to another challenge. If I've got memory all filled up, but as you can see, I'm still missing a page of process 1, and I'm missing a page of process 2, and I need one of them, perhaps by process 2 going down from page 2 to page 3, I'll get an interrupt, but now it's not just a page fault, it's a page swap. A page swap happens when I need a page for a process that's not in memory, and there's no free frame to put it in. They might say, well, why don't you just wait until somebody's done and a page can be freed up and then you can use it? Well, that's okay, except remember I said I don't need to have all of my process loaded in memory. So maybe I'm the only one in there. I'm just not all in yet. I can't wait for myself to be done to get a new page because I need my new page to be done. So in general, I'm going to have to replace something. So when I need to swap a page out, I again have to make a decision, and I need to think about what's fair. Well, lotteries are fair. Maybe I should just pick a page at random. Swap that one out, swap the next one in, go on to the next. Well, the problem with that is it can be really inefficient if I happen to swap at random one that I'm going to need next. Maybe what I should do is set up a queue. The page that's been in memory the longest is the one I'll get rid of. I would need to keep track of when that one was loaded, so the operating system again has got some more work to do, but that seems fair. On the other hand, it could be really inefficient. If that's the code that's monitoring the internet for your Facebook, and it's doing a lot of work continuously, I wouldn't want to swap that one out. I don't want to swap out your English paper or something useless like that. Maybe I should look at what's been going on recently, and stuff that hasn't been used in a long time, kind of like the stuff at the bottom of your closet. Get rid of that if I need a place to put my new pair of blue jeans. Least recently used. This means I got to keep track even closer about what's going on because I got to keep my fingers on every time a page is being used, not just when I'm loading it. One other problem here is some of those pages have memory in it that I write to. Remember, it's all stored in the same memory, programs and data. If I write to a piece of data, I've changed something in memory. I can't just load something in over the top of that, or I'll lose what I changed. So for a dirty page, I'm going to actually have to write it back out so I can bring it back in when I need it again with the right data values in it. So modern operating systems do take advantage of the clean and dirty issues. Many of them use a variation on least recently used, but there's still an awful lot of active research going on as to how to best model programs so that you can figure out what's the most efficient way to be mostly fair. So this technique is known as virtual memory. It allows us to run programs that are bigger than the physical memory available, and the sum of all the programs that I'm running could be even bigger than that. I store out-of-memory pages in a page file, and ideally I give that some priority access on the disk. We'll talk about that later on. You can see here in Windows, there's actually a file. It's a hidden system file, so you have to know how to look at those in Explorer. But it's called pagefile.sys, and it's usually sitting in the root directory of your C. If you know what you're doing, you can play around with it. If you got multiple disk drives, spreading it out across multiple disk drives can make things a lot happier on your system. You can also make it bigger so you can run even more stuff than you have memory for. Now, it can also lead to trouble. Trouble is called thrashing, otherwise known as too frequent page swaps. Let's take our two programs here and see how that works. Now, this is artificially constrained to a very small memory and two very small programs, but you can see how the same thing would happen for large systems, and in fact, your lab, you're going to try and make it happen on your own personal computer. So here I am, operating in process 2, and I need to get page 3. Well, let's say we've been just operating in order, and so the longest page in there is page 0 from process 1. So we'll swap him. All right, now page 1 gets a chance at the CPU. He needs his page 4. So we'll swap out page 0 from the other. All right, we've reached the end of process 2, and he's doing a loop way back up to the top to his first page. All right, let's blow away page 1 from the green guy. Alright, page 1 is doing his next process and he needs page 1. So we'll blow away page, I guess, page number guy. Son of a gun, that's just the one I needed next. Oh, and now process 1 needs his page that I just swapped out. Well, you can see what's going on in here. We're chasing our tail, we're spending a lot of time swapping pages in and out of memory and not getting very much work done in the process. Now, this is due to a least recently used algorithm, but you could invent situations where any of the other algorithms would have the same kind of trouble. In a sense, we're just trying to do too much for the amount of memory. So thrashing shows up as you see your load on your processor increase. You can watch your CPU utilization go higher and higher and higher and higher. And then at some point, when you've got too many programs fighting over too much memory, the system slows to a crawl, but your CPU's not doing much. Who is doing much? Your disk drive, swapping stuff like crazy back and forth to memory. Thrashing. So let's summarize memory management. Quick and easy, one partition keeps the operating system and the program separate, and we use a base register or some tricks in the loader to map logical addresses to physical addresses. Multi-programming with fixed partitions to support multiple processes. Now, the cost is all our available memory may not be in one place, and so we've broken up the ability to run larger processes or optimize how much memory we're using. Variable partitions give us more efficient use of space, but take more overhead because I got to check whenever I'm running past the end of my partition. Paged memory lets us split a program up and gets the most efficient use of our memory, but our programs can still be too big. And we have to have this whole page mapping table and interrupts and all sorts of other mean and nasty stuff going on to make it work correctly. If we're going to do all that work anyway, let's go ahead and implement virtual memory that allows larger processes than I actually have physical memory for. This means I got to get demand paging working, but it also means I can thrash myself to death. Let's go back to history for a minute. Why did I go through all that history? Well, if you start way up in the left-hand corner, you'll see that what happened was we evolved from single-user systems that are actually off the top of the screen down through the stuff that does virtual memory between 1960 and, the end of the 1970s in the IBM environment. They were actually the first people to take that evolutionary step pretty much through the pieces we just went through. On the personal computer front, we traveled the same journey, starting with something really simple and then going to something that's really complicated. Windows NT and Mac OS X, or Windows 7, even worse. And now we're seeing the same thing happen in phones. You guys are going to have to worry about what happens after phones, but the difference between Symbian and BlackBerry, who are losing market share, and Windows, iOS, and Android, who are gaining market share, is those latter three have implemented virtual memory, and the first two didn't. So you might ask yourself, are we seeing this sort of repeating spiral as everything's getting more and more powerful, and we're just being able to leverage by standing on the shoulders of the giants who have come before us to invent new and groovier systems for more and more powerful things? Or are we chasing our tails? That's up to you.